All right, so let's come back. There are several questions, so let me answer one by one. So one moment. Okay, so there's a question is about like, if I understand correctly, she's asking about just like, because each process has their own process descriptor, so is there any integrity issue there? So actually you can think about process is a concept about to try to become high isolation. So in most cases, process is a safer way because they have their own isolated resource there. So for this question, I would say usually process has great integrity, sorry. So the other question is about IO things. So I would say like IO thing will be introduced later, several few weeks later. So I think for the IO things, yeah, let's wait for the interrupt and then the IO service here. And okay, coming back to the copy on write. So the question is, will the kernel record about, for example, for this patch frame, how many process share with this patch frame? Yes. So actually there is a counter here to keep track of how many process share the like this patch frame. Okay. So if the counter doesn't count to one, actually when there is a write operation and then there will be a new patch frame will be allocated. Okay, but if this frame, if this frame is only belonging to one process, what I mean is if the counter becomes one, then we don't need to do the copy. Okay, you can just directly modify this patch frame. Okay, so if this is the last frame and there is no one to share with you, then you can just directly modify it. But if there's not, for example, if the counter becomes 2 or even more than 2, then we will copy out the new patch and then to modify the new patch. Okay, so this is the concept of the copy on write. And I think it's on the same patch is here. So people are curious about why here we write 4 label here. So long story short is because current Intel use 4 label patch table. So usually there is not only one patch table here, there are a lot of labels here. So you can think about there are several patch tables here in current Linux. And we will go through this during the memory management topic. And there's another question is about when will the process set their state to the text uninterruptible. So in most cases, the uninterruptible state will be set in the one moment here. So for the text uninterruptible state will be set during the fork. So when we are going to fork out a process, we will use this state because we don't want any other signals to interrupt this fork kind of procedure, because this is the initialization stage. So this is a super spatial state, I would say, because in most cases, if there is an IO service like this kind of things, people are using this interruptible state. Okay. How many kernels are running on a 4-core processors? Is it 4? Okay, so I think I should put it like this. So as you know, like kernel is just like a bunch of like kernel functions there. So you can think about it is also possible. If you have, a multi-core systems and each core run one like scheduler and the other run other like memory manager, it is also possible to do like these kind of things. Okay. So, yep, that is for most questions. Let's come back to the scheduler part. Okay. Okay, so I think we stop here, just like we're wondering how to decide the time slice and then how to decide which process should be run next. So the time slice definition of the time slice is the time between when a process starts to run and the process being interrupted or like being preempted. So this is called time slice. Okay. So process priority. Actually, each process has their own priority, right? So usually in Linux, we use a thing called nice value to represent what is a priority for each process. So a larger value represents being nicer to others. So you can think about larger value means lower priority, okay? Because it being nicer to others, so the process will give up more kind of resource to other, okay? So lower priority usually means normal process, okay? So why I say normal process for low priority, because there are some other process called real-time process, like kernel process, and then those kind of process, actually they have higher priority. Okay, we'll talk about it later. Okay, so real-time means like we want to make sure there is one process that can finish before one like timing. So this is called real-time. So there's hard real-time and soft real-time, and you can think about just like this process should have their kind of should have their criteria to say, I want to finish my process, for example, in 1 second. So if we don't want to fail this 1 second assumptions, then they usually should have higher priority so they can preempt lower priority process. Okay. Okay. So on the right hand side it is a really kernel version is Linux 2.6, but I think this is quite representative for this example. So you can see like there are nice value from 19 to -20. So as I say, larger value means nicer to others. Because you are nicer to others, so you don't want to occupy CPU for too much of time. So nicer to others, it means like you have higher like 19, for example, then the time slot you can get is only 5 milliseconds. So 5 milliseconds means like for each 5 milliseconds, you need to switch out to other process. You need to release the CPU to other process. So you cannot run more than 5 milliseconds. Okay. So for the higher priority process, like -20. So -20 is the smaller value. So usually this will be the highest priority process. So -20, it means you can get 800 milliseconds for time slice. So 800 milliseconds means like it can run for a super long time. It is around like 160 times longer than 5 milliseconds. Okay, so you can think about longer time slice means the process will occupy CPU and the memory for a longer time. So you usually will run faster to finish their process. Okay. Okay, so actually on the right-hand side, we call this called static mapping. So static mapping is because, hey, if we say this process, the nice value of this process -20, then it will directly get 800 milliseconds. So if one day the system administrative set the process to 19, the lowest priority, then its time slice will simultaneously change to only 5 milliseconds. So there is a one-to-one mapping between the nice value and the time slice for this static mapping. So later you will see, actually there is another thing called dynamic mapping. Just like the time slice will not be decided at the moment you get a nice value. I mean, there are some criteria there, so the nice value, sorry, so the time slice will be fluctuated. Okay. So for this static mapping, actually there are two challenges. The first challenge is triggers context switch frequently if all processes are low priority, right? Because the nice value of these kind of things, usually they are given by the system administrative. So usually for those high priority, I would say larger than 0, usually normal process will not get this nice value. Because those nice value larger than 0, they are given to the, for example, kernel process or like real-time process. So in most cases, you will see your normal process will have a nice value lower than 0. Okay. So probably maybe it's something between here. So usually you will say maybe most process you can get nice value like 9 or 10, for example. So here comes the case. If all the process only get 10, it means each process will be rescheduled in 5 milliseconds. Okay, but this is super time. This is super high overhead because for every 5 seconds, CPU should run a process context switch. You need to switch in all the process and switch all the current process. Okay, so this is the first issue. Just like CPU needs to do frequent process context switch if most of the process they are in a low priority. And the second challenge is about the time slice difference is huge for process with higher nice value, which means low priority process. So what does it mean? Let's do some calculation here. So if you are the high priority process, you'll get, for example, nice value minus 20 and minus 19, right? So let's focus on minus 20 and minus 19. So actually the time slice is 780 milliseconds and 800. So it means the difference is only 20 milliseconds for the high priority process. It doesn't really feel too much of difference because, I mean, if you can get 800 milliseconds, even you have, I mean, even you only get 780, actually there's only kind of, I would say like 5% reduction here. So it doesn't really matter that much, right? But the thing is, if you are a low priority process, you only get nice value 19 or 18, it matters a lot because 19 can only get 5 milliseconds, but 18 you can get 10 milliseconds. So when you compare 5 milliseconds to 10 milliseconds, actually it is twice more times, right? So it matters a lot. So it will lead to the resource unbalance issue. I mean, for low priority process, their time slice has a huge gap there. Just like for lower priority, you will have like twice of the difference time. But for high priority process, it doesn't really matter that much. No matter minus 16 to minus 20, actually, it doesn't really have too much of difference there. So how to deal with these two challenges? There are kind of Linux kernel scheduling they are thinking about. So we will introduce three, Linux kernel scheduling. So one of them called CFS is from 2.6. It's quite familiar. It's quite famous in the past years, and CFS can solve most of the issues here. Okay, but I'll introduce from the historical one by one. Okay, so after finishing time slice, there are also several characteristics related to the process scheduling. The first is I/O bound or compute bound. So I/O bounds means it spends much of time submitting and waiting on I/O request. So for example, keyboard, network, storage, they are most of them they are I/O bounds. So like graphical user interface, the GUI things. So GUI things is when you type something, then on a keyboard, then on your screen, you will see something will pop up, right? So for a keyboard, maybe you type 1 to 10, then the monitor will show 1 to 10. This is the GUI things. But actually, GUI is usually I/O bound because it doesn't really do too much of computation. It only shows the things you type to the keyboard. Okay. So the policy for usually for I/O bound is to run more frequently, interactively, a shorter time slice, right? Because what we need is interactive. Because when you type the keyboard, you don't want to wait for like 1 second or even 10 seconds for the for the things to show on the monitor, right? But it doesn't really need too much of time slice because it doesn't really use too much of CPU resource here. For time slice, it can be super short because we only need to fetch the data in the buffer and then show them on the monitor, and we are done there. Okay, so this is for I/O bound. So you have I/O bound, it means like there is another opposite is processor bound. So processor bound means to spend much of time executing code. So usually like SSH key generation. So like if we are going to generate a SSH hash, then it needs to compute a lot of things, or maybe like MATLAB. So you are going to do some mathematical things. Okay. So for for this kind of process, actually it runs less frequently. So what I mean less frequently is compared with this kind of keyboard things. Because keyboard you type very frequent, right? But compared with the SS key gen, usually you will not gen a key so frequent, right? So this is just like the comparison there. And usually because you are processor bound, so you need longer time slice, right? Because you want to generate a SH like SHA-1 hash there, so you need CPU to run for a longer time. Okay, so here's just a decision to let you know, like, not really like all process need a lot of CPU resource. There are some process actually they need more about interactiveness. They need more process to release the CPU resource out to them, and maybe they just need 1 millisecond or even less to finish their task. Okay. Okay, so the last thing to let you know is actually when we are going to design, actually there's not only the scheduler thing, actually in the entire kernel or even in other systems, overhead is quite important. Just like, for example, when we are going to find the next process, there are several tons of data structure you can do these kind of things, right? There are queue, there are tree, there are bitmap. So different data structure, they have different complexity there, and they have their pros and cons. So how to pick a right data structure for this scenario is a critical thing. Okay, so there is one interesting thing is, when we are going to pick the data structure, there is also how to implement the data structure, right? So complexity is one thing, but for example, if there is a global run queue, or actually there is a per processor run queue, actually it also matters a lot. Because, for example, if there are several processors there, then for all the processors, they share the same global run queue. So for one processor, they are going to get the maybe process out from the run queue, it needs to lock the queue. So other processor will not access this global run queue. So it will take a lot of time for other processors to use this global run queue, but it is easy to implement, right? People usually like the global things, because global just like you can assign a global parameters and you don't need to take too much of time to rewrite your program. Okay, so this is about the global things. All right, so those are all about the criteria. So let's now give you some example to let you feel like how Linux design their own scheduler. So let's start from the very beginning, kernel version 2.4, and this is a single one. People call them big O-N. Okay, so it is quite simple. All processors share a global run queue, or you can think about to share a ready queue. And it's sort of processed by their priority. So it is quite easy, right? When there is a process add into the run queue, and because maybe they will get a nice value and they will get a time slice, so we can do a sorting, and we will always pick a high priority process out from the global run queue. Okay, and there are several kind of bad things for this design. First of all, system should lock the run queue when a process run out of its time slice. Okay, so when one process is finished and it is going to pop out from this run queue, actually, system should lock this run queue. And because this is a global run queue, so when the run queue is locked, then no other processor can access this run queue. So all the other processors, if they're going to run a scheduling, they will be busy waiting here to wait for this run queue to be released. Okay, so there is another thing is process should be inserted to an expired queue in order. So it means like if we are going to like insert the process, no matter in the run queue or in the expired queue, we need to do, for example, the sorting things. So it takes a lot of time if there are a ton of process. I mean, if there are only 5 processes, it doesn't really matter. But I mean, if there are like thousands or even 10 of thousands of processes there, each time when you are going to do the sorting, it takes a lot of time, right? So this will be the case. If there are too many processes and you use this ON, then usually probably you'll get ON of time here. okay, because you need to do a sorting, okay, and maybe more. So we need a faster one. So in the kernel version 2.4, they introduced a faster one called O1. So O1, just like their name, they're going to let the scheduler to run like O1 of time, super fast, right? So how to implement these O1 things? Actually, there are two data structures here. So first of all, is there is an active bit array. Okay, so what do I mean for active bit array? So actually in Linux, you can think about there's nice value there, right? So if, for example, there are 140 priority here, so you can think about maybe there are 140 nice value, but actually you only see 40 here. I will let you know there's another 100 later. So in summary, if we have 140 level of priority, so each priority will get 1 bit, okay? So each bit will be set if the corresponding process is added to the run queue. Okay, so for example, you can think about this is the, for example, highest priority, and this is the second highest priority. So if there is a process, it is second highest priority, and it is added into the run queue, it's added into the ready queue. So once there is a process inside, we will mark here. Okay, so the O1 runs like it checks active array to get the target priority value. Okay, so after getting this target, I would say bits. So this is second bit, right? So actually they will have another data structure called active array. So because there are 140 bits here, so actually there are 140 active arrays here. So this is Q0. Q0 is for the highest priority, and Q1 is for the second highest priority, right? So when there is a process, or like people call it text here, when there is a process added into a ready queue, we will use a chaining to chain them in the queue. So for the queue, in the same queue, they will be in the same priority, okay? So in this case, if we are going to get the next to be scheduled process, what we are going to do is to check from the leftmost, because this is highest priority. So there is no one in the highest priority, right? Because there is not set it. And if you are going to check it, to double check it, you can just check the active array. Actually, there is no process in the topmost Q0, okay? It means there is no highest priority process they are going to be scheduled. Okay, so we will check for the second one. Okay, so second one in the bit array, this bit is set, right? So because this bit is set, it means in the active array part, the corresponding queue, there are some process inside. I mean, there may be one, and maybe there are more than one. They are all possible. So we use a FIFO to get the process out from this active array. So using the FIFO, we will get a text one out, and then we will say, hey, let me schedule the text one. Okay, so this is just a way to implement O1. Okay, so coming back to the question, why this is called O1? Why it is possible to do it O1? I mean, we still need to check for the bit array, right? So the reason is, here are some tricky things. Actually, for this bit arrays, it cannot be any bit arrays. It should be tailored for a CPU. So in a CPU, there are some spatial instructions here. So for example, the reason for this rule is 32 bits is because for each instruction for CPU, it can read for these 32 bits together at the same time to the CPU. Okay, so after reading the 32 bits into the CPU, there is instruction. There is an instruction in CPU can fastly get the leftmost bit out. Okay, so with this CPU instruction, we can quickly know which bit is set. Okay, we only can know where is the first bit is set in this 32 bits array, or like in this 32 bits bitmap. Okay, so it relies on CPU's kind of accelerations to quickly get out where is the first index that is set. Okay. Okay, so we only talk about the insert part. So actually there is when the process use up the time slice, right? So we need to recalculate the priority and enqueue to the expired bit array. Okay, so you can think about, actually, here is the active bit array. So we need the same one, but they are for expire. So expire means like the process use up all the time slice, right? So, but even the use of their time slice, they still are not finished. So they need to put to other place. So other place is, it will have the same one. It will have the duplicate one, but the name will be expire bit array. So because we have the expire bit array, so it means like we also have the expire array for this one. So you can think about this pair of the data structure, they have two. Okay. So one for active one and the other pair for expire one. Okay. So for this design, why we need two? Because when no bit is set in the active bit array, we just directly switch active and expire bit arrays. So we are finished. Okay, so we will schedule all these kind of process out, and then when this active array, there is no process in the active array, and for the left-hand side, the active bit array part, if no bit is set, then we will switch this bit array, we will switch this active set to say, hey, that will become expire one. So the expire one will become the active at that time. Okay. So we can then resume the scheduling, and then we can use the original expire bit array to become the active, and we can do the following scheduling. So in this case, actually we only need 4 data structures: one active bit array, one expire bit array, and a corresponding active array and expire array. Okay. Then we can finish this O1 scheduling thing. Okay. So question? Oh, okay. So the reason for there are 4, because you can think about this bit array is only for the active, but you also need another one for the expired. So we will have one bit array for the active and the other bit array for expired, and then also for the active array. So those active array here is only for active. So we will have another set, another Q0 to Q139 for expired one. So this is the reason why I said we need 4. Yep. Okay. The reason is, okay, one moment. Okay, the reason is in Linux, here from 19 to -20 here, there are 40, right? 40, they are for normal process. And there are a set of 0 to 99, I mean, nice value, they are for real-time process. So in total, they will have 140. So there are 140 priority for normal process plus real-time process. Okay, but in this table, I only show you the normal process part. So actually, this 140, it depends on how many priority level they are. I mean, if you change the kernel code to assume there are, for example, 200 priority level, then this 140 bits should be changed to 200 bits, like this. So it is customizable. Okay. Okay. So okay. So what is the drawback for this O1? Actually, there's a one really huge drawback is it has low interactive performance, right? Because you always start from checking on the first rule, and then the second rule, and the third rule. And the first rule only has contained the highest priority process, higher priority process. Okay, so when it comes to the later, this will be the lowest priority process. So for example, if there are always new process being created, and if the new process has higher priority than the last one, then the last one will never be scheduled. Okay. So this is called low interactive performance, because the last one will never get the chance to be executed. Okay, so it is not really fair. I mean, it is good for high priority process, but if you are a low priority process, probably you will get the CPU resource. You need to wait for a super long time. So I'm going to introduce another one. Is the start to use begins kernel version 2.6. It is called completely fair scheduler. Actually, this completely fair scheduler, you can see like O1 is before 2.4, O1 is 2.5, and CFS is 2.6. So they are in a similar times. Not really similar times, but I mean, they're close to each other. So CFS used for a super long time. If I remember correctly, the latest scheduler is after kernel version 5, something like that. So CFS used for a super long time. It's for like several 10 years here. Okay, so CFS, the goal for CFS is to make the scheduler more interactive and more fair than O1. Okay, so here are two concepts. The first is, instead of statically mapping time slice, each process would receive 1/n of the processor's time, right? So actually, let's say about like static mapping means like no matter how many processes they are, if they have high priority, they can get a lot of time slots, right? But if there are too many processes, it means lower priority has literally no chance to run the process. So a way to solve this problem is, why not just say, for example, if there are 10 processes and these 10 processes need to be run, for example, each second. So for each seconds, the 10 process just share this 10 seconds. Sorry, to share this 1 second. So you can say maybe high priority process, they can get like half of the second, but the rest of them, they still need to be scheduled in for the rest of the half seconds. So every process can be run in this 1 second, and then we will start for the next second. Okay, so it means like we can make sure all the process can be run in this predefined time slice. Okay, so the other thing is to schedule process for infinitely small durations. So this is also to deal with the static mapping, because static mapping, like if there's no I/O, in most cases, we will reschedule them when they finish their time slice, right? But the same thing, high priority process get too many time slice. They're too long. So if, for example, we only have, for this 10 process, you can only run it inside 1 second, then for all the process, they will be rescheduled in the inside of 1 second. Okay, we'll have more example for this later. So we need to first define one thing is called virtual runtime. So virtual runtime is the real system runtime plus priority. Okay. So we're going to keep the virtual runtime of all running process the same. So here is a calculation here. So virtual runtime equals the delta execution times nice wait over nice k wait. So it is quite complex. I mean, it is just like delta execution is the period to enter scheduler. So as I say, if there are 10 processes, you can say I want to reschedule the scheduler each 1 second. So this is called the delta execution. So we have n process, and we are going to reschedule them in how long. And in Linux, this is a constant. Usually it's 0.75 milliseconds or 6 milliseconds. So for each 6 milliseconds, no matter how many processes you are running now in the systems, they need to be rescheduled again. Okay. So nice wait over nice k wait, it is just for like, for each process, they have their nice value, right? And nice k wait means we are going to sum up all k running process. Okay, so this is about the fairness, because just like, for example, nice wait maybe for the first process is 1, and then for the overall k process maybe is 10. So we can get 1/10 of the delta execution for running. This is for the first process, and then maybe for the second process, this nice value get a little bit higher, like 2. Then you can get a little bit more for the time slice. Okay. So, but the problem comes here, just like actually nice weight here, it is possible to get the floating point, right? Because this is smaller and this is larger. So here is a floating point. And then in Linux, they are going to support these things because there are some cases like some CPU doesn't have the floating point unit. So if you're going to trace a Linux code, you are not find this formula. What you will see is here, the practical one. So you will see like they are going to times the 2 to 32 and then they will ship the 32 things. The reason is if they times the 2 to 32, and then for this calculation, they can try to avoid to touch the floating point. Okay. And then there are some tricky way to let them ship back. So this is just a practical to let you know if you trace a Linux code, you will not really see this theory one. You only see the practical one. And this is the reason because Linux want to support those CPU doesn't have the floating point unit. Because CPU, if there's no floating point unit, then you will take a lot of time, usually 10 times or even more times for running these floating point operations. Okay. But I mean, this is not important. I mean, in the exam, I will not say, please explain why like these kind of things. Okay, so don't worry. So after doing the calculation, so each process will get their virtual runtime, right? So virtual runtime, the smaller one means like it most need of CPU, and a larger one means least need of CPU, like this. So they use a red black tree to maintain all the virtual runtime for each process. So the reason to use red black tree is because it is a balanced tree, so it can control when they are going to find a process, which process should be scheduled next. Actually, they can directly get the leftmost node in log n time. So this is the reason why they are using red black tree. Okay. Okay, so let's focus on the theory formula. So we say we are going to time the nice weight over nice k weight, right? And the reason for this one is to make the scheduler becomes more fair. Because for this part, it means if all the process is going to share this delta dash execution time, for example, 6 milliseconds, then how much can each process get? So it depends on your priority. If you get higher priority, maybe you can get half of them. For example, you can get 3 milliseconds. Okay, but we can make sure in these 6 milliseconds, all the process can at least touch the CPU once. Okay. But here comes the problem. How to decide the weight? So remember, we talked about if we use static mapping, the question is for the low priority one. Let me remind this one. So if we use static mapping here, it means given you a nice value, we can quickly get the time slice here. And then for this case, there is a resource unbalance because for low priority process, the time slice is so huge. I mean, the gap is huge. There's 5 milliseconds and there's 10 milliseconds, right? It is not that fair. So for CFS, they're trying to solve this problem. So what they're using is called a 10% effect. So if you open up your Linux source code, you will see something like these kind of things. This is just directly screenshot by the Linux kernel 4.4 things. So let me just give you some hints about why there is a thing called 10% effect. So there is a priority. So 0 to 40, right? So there is minus 20 to 19. So here are all nice value from 19 to minus 20. Okay, so this one is for the process getting nice value 19. It can get, for example, 15 milliseconds for running. Okay, and then here is like at 761. Okay, so not really is millisecond because actually this is kind of for weight. So, but I'm going to analog to the static mapping. So you can image like this is just like very close to the time. Okay, but I'm going to emphasize this is not a time because the virtual runtime show time the delta execution. It will become time, and here there are only weights. Okay, so you can see like for the 15 and 18, actually the difference between them there is only 10%. Okay, So if you, as I show, like for the static mapping in the traditional version, there will be 2 times larger. Okay, so not only the low priority process, also the high priority process. If you do the calculation to do the calculate for the topmost 2 priority here, actually the difference is also 10%. Okay, so for a high priority process and low priority process, they look fair for getting the weight value. Okay. And maybe you will have a question about, so how to get this kind of weight value. Actually, there's a lot of calculation. I'll not show here, but if you are going to get the value out, actually there is a quick mapping here. So the weight, how to calculate the weight is like this, just like there are several nice value here from 19 to -20, and here is a priority, and you can get the weight value from given a nice value, and here is a calculation way to get the weights here. Okay. Okay, so I think that is for the CFS. So let's call it a day. So see you guys next week for the real-time scheduling part. Thank you.